Hey guys, Dr. Brown here with Kubo Math, and today we're looking at area, specifically the area bound between two curves. Okay, if I can get the top off my marker here, we'll start. All right, let's say we have a curve, looks like that. So we have y and x, and we're looking at that integral, the area under that curve from 0 to a. We would simply integrate from 0 to a, whatever that function is, f of x dx, and we would get that total area. Well, what if I have another curve and it looks something like that? It's a little different, but it looks like this. But also from 0 to a, so I could integrate that. So I could integrate g of x dx from 0 to a, and I could get that area. But what if I said, what's the area bound by those two curves? So I need to know this minus that area. So if I put those two curves together, one curve like this, the other curve like that, that total area minus that area, so that area minus this one's area equals the remaining of what's left. So now I could take from 0, integrate from 0 to a, f of x minus g of x dx, and get the area bound by those two curves. Now you'll notice they intersect here and they intersect here, so it gives me a closed area, a bound area that I can work with. So let's look at the function that we have here. We have x equals y squared minus 1. We want to know the area bound by x equals y squared minus 1 and y equals x minus 1. So I'm an old school graphing guy. I like to graph things. Now I notice in the new textbooks, just use your graphing utility to graph this. Well, back in the day, this was our graphing utility. It was a piece of paper, pencil, and we would say, okay, I have values of x, and I have, well, I need to solve this one for y. So x plus 1 equals y squared. So y squared equals x plus 1. Y equals plus or minus the square root of x plus 1. Okay, so I would say x, and then y equals x minus 1, and y equals plus or minus square root x plus 1. So then I would say, okay, negative, I'm going to let x equals negative 2. So negative 2 minus 1 is negative 3. Negative 2 plus 1, okay, that's a bad one because I have a complex number here, so let's not go with that one. Let's go with negative 1. Negative 1 minus 1 is negative 2. Now later in calculus you'll keep going because complex, hey, let's rock on, but not now. All right, so now this one, negative 1 plus 1 is 0. So now I'm at 0. All right, so let's go with 0. 0 minus 1 is negative 1. 0 plus 1 is 1. The square root of 1 is plus or minus 1. So let's go with 1. 1 minus 1 is 0. 1 plus 1 is 2. So now I have plus or minus square root 2. 2 minus 1 is 1. 2 plus 1 is 3, so now I have plus or minus square root 3. 3 minus 1 is 2. 3 plus 1 is 4. Square root of 4 is plus or minus 2. Now you'll notice at negative 1, negative 1, these two curves are the same. When x is 0, negative 1, those two curves touch. Matter of fact, let's just graph. Oh, well, by the way, 2 and positive 2, they touch again. 2 and positive 2. That's when x equals 3. The y value is 2. All right, so we have -1, -2. And let's just keep going with that one. We have 0, -1. So 0, -1. 1, 0. Actually, that's enough data to get a line. We'll go ahead with 2, 1. And 3, 2. 1, 2, 3, 1, 2. So that's one curve. Actually, that's the line, okay? Let's go with the other one. -1, 0. 0 plus or minus 1. So x is 0 plus or minus 1. So that's my points here. 1 plus or minus square root 2. 1 plus or minus 1.4. Somewhere in there. And 2 plus or minus square root 3. So that's 1.7 or so. 1.7. And then 3 plus or minus 2. 1, 2, 3 plus or minus 2. So this curve looks like this. So the question they're asking us is, what is the area bound by those two curves? Now, we just learned, I'm going to erase this right here. Earlier we said, wow, I could have f of x minus g of x dx, and I could integrate that from a to b. So I could integrate that from x equals -1 to x equals 3. But whoa, big guy, hang on. When you integrate that, I would encourage you. Now, I look at things in super simple form, okay? If I drew a differential rectangle inside of that, for a given value of x, this is what goes through my mind. For a given value of x, what are the y high and y low? Well, I would have that value of y and this value of y. So in my mind, the high one's my f of x. The lower one is g of x. But I continue to slide that differential all the way up and down to make certain that the high one is this curve and the low one is that curve. And that works just fine until I get down here. Oh, what's YH? Well, it's this curve here, right? I'll just call it YH. What's Y low? Oh, it's not this curve any longer. It's the negative. So Y was plus square root x plus 1. And this lower section is minus square root x plus 1. So now I have this situation. And this would be from this integral. Actually, we'll just set it up. If I want to integrate on x, I have to look at this f of x minus this g of x from x equals -1 to 0. So -1 to 0 of square root x plus 1 minus what? Minus what? A minus square root x plus 1. Don't get hung up that this minus is that. It's not. I love putting the parentheses to say, okay, my formulation says f of x minus g of x. What is g of x? It's minus square root x plus 1. dx. Now that gets this area plus the integral from x equals 0 to x equals 3. Remember, this was the 0.32. This is the point -1, 0. This point was x equals 0, -1. So a lot going on here. So now once I get beyond this area, I'm back to the original f of x and g of x that I had earlier. So f of x then was plus the square root x plus 1 minus what? Minus g of x, which is x minus 1 dx. I don't want to do it that way because there's a lot of integrals to work with. And now these are simple, but they could be complicated. So why not do the dreaded d of y? Let's do that. Okay, let me clean this thing up. Sorry for all the messiness here. Okay, let me clean up some of these things. Oh, need to keep that. 3, 2. All right. What if we drew our rectangle this way? For a given y, this is my thinking now, for a given y, what's the highest value of x? That's my x, the high x, and this is the low x. If I slide that differential rectangle all the way up and down this, you'll see for a given y, all of these, the top of the rectangle is off of this curve, the bottom of that rectangle is off of that curve, all the way up and down. Which is awesome because now, let's see, let me solve this for x. I need x equals f of y. So y plus 1 equals x, or x equals y plus 1. And this one I was given x equals y squared minus 1. We were given that. So those are my two functions I'm dealing with. Remember, this is the line. It's x equals y plus 1. So this is y plus 1. And that's going to be my f of y because it's the highest x for a given y. That's f of y. This one's going to be g of y because for a given value of y, it gives me the lowest x. It's y squared minus 1. So now let's integrate this thing. We have the integral from y equals what? When I'm looking at this, the lowest y, -1, all the way up to y equals 2. So -1 to 2 of f of y minus g of y dy. That's what we're working with. F of y, just going to plug them in here, is y plus 1 minus what? Minus y squared minus 1. Now I'm going to remove the parentheses and distribute that negative. All that's dy. Put that around like that. All right, I like to keep my highest power terms first. So -1 to 2 of negative y squared plus y plus 2 dy. So I have one integral, not two. Simple enough. Okay, I increase the increase this by 1. So 2 plus 1 is 3, divide by 3. So I have minus y cubed over 3 plus, that's y squared over 2, because that's y to the first power, add 1 equals 2, divide by the 2, and plus 2y. All of this from -1 to 2. Okay, we're going from -1 to 2. Clean out a spot to work here, I guess. Well, I'll do one row here. All right, let's put 2 cubed is 8, so -8 over 3. Matter of fact, let's just move it right here. I'll be off the screen, but you don't need to see me anyway. -8 over 3 plus 2 squared is 4. 4 divided by 2 is 2. Plus 2 times 2 is 4. Minus what? -1, I'm going to cover up this negative. -1 cubed is -1. And that makes it a positive. So positive 1/3 plus -1 squared is 1. 1 over 2, that's plus 1 over 2. Minus, or 2 times -1 is -2, so it's minus 2. What do we have? A 3 and a 2. Let's make everything over 6. Well, let's do it this way. 8 over 3, -8 over 3 times 2 over 2. Plus 2 over 1 times 6 over 6. Plus 4 over 1 times 6 over 6. Minus what? 1/3 times 2 over 2. That's going to give me 2 over 6. So let's go ahead and do that. I'm running out of room. 2 over 6. And this one's going to be 3 over 3. So that's 3 over 6. So it's plus 3 over 6. Minus 12 over 6. All right. So all of this is going to be over 6. -16 plus 12 plus 24 minus 2 minus 3, negatives positive, plus 12. All right, I'm going to clean this up here. All right, -16 plus 12 is -4. -4 plus 24 is 20. 20 minus 2 minus 3 is 15. 15 plus 12 is 27. 27 over 6. So that's 9 times 3 over 2 times 3. 3's cancel. So I end up with my area is 9/2. And we were able to do that by understanding, writing the differential rectangle and making certain that the top of the rectangle and the bottom of the rectangle, they go along in the same, follow the same f of y, g of y, or f of x, g of x as what you're thinking. Because when we were dealing with our rectangle sticking in a dx perspective, we had to create two different integrals to be able to get the area under those two curves, bound by those two curves. So the area bound by those two curves is 9/2. Hopefully this helps. Why are we doing this? Together we're trying to build a better tomorrow. And do that how? Do that through math. Okay, that's all for now. Keep studying. We'll talk to you next time. Thanks.